Hello, this is Eishi Arima from TOOM. In this presentation, I'm going to talk about optimization for hardware resource partitioning and job allocations on modern GPUs and the per caps. This is a collaborative research across TOOM and LLZ. And here is a summary of this talk. Our focus is, in the first place, optimization for resource partitioning, job allocation, and per capping, especially on our real GPU chip. And as an example, we use NVIDIA MIC that partitions our chip at the granularity of GPC, that is a kind of coarse-grained partitioning. And our key observations here are, our first one is chip-level scalability highly depends on the compute and memory intensity, and also types of operations, and also power cap setup. And also memory partitioning option matters, such as private or shared lower level memory hierarchy. And our optimization here is hardware setup, job mapping optimization for a given application pair as a function of application characteristics, and that also we use a predictive performance model here that consists of problem definition, systematic solution, and statistical modeling using linear regression. And the evaluation results basically really good. And here is the outline of this talk. Okay, let's move on to the background. GPUs are now commonly used in top-class supercomputers. About 160 systems in the top 500 lists are GPU equipped, and also the power consumption is becoming more and more significant problem in supercomputers. So if we look at top-class supercomputers, power consumption can be over 20 megawatt, and we need to care about that. For that, we target power and resource management for GPU-based heterogeneous HPC systems. If we look at the literature, usually hierarchical power resource management are used. Let's say we have a central power governor that distribute node level power limit, power cap. At the node level, node power manager set up power cap to each component accordingly, so as not to exceed the node level power cap given by the central power governor. And at the same time, we also consider co-scheduling here. Co-scheduling means collocating multiple applications at the same node. That is kind of promising approach to mitigate the waste of resources. For instance, memory-intensive applications usually don't fully utilize compute resource. Mixing compute and memory-intensive application and collocate them makes sense to maximize resource usage. And in particular, we focus on the GPU resource partitioning and power capping in this study. And if you look at the state-of-the-art GPU chip, as an example, NVIDIA A100 that has power capping feature, and one can set power cap. And also that also supports a MIC feature that enables GPU partitioning at the granularity of GPC. GPC stands for Graphics Processing Cluster that consists of tens of stream multiple processors. And each of SM includes tensor cores, FPUs, etc. And one A100 chip consists of 8 GPC like this, and that can be partitioned like this. And one SM is here, and that consists of multiple computing units. And we consider these different types of computational units as well as memory bandwidth utilization to optimize partitioning, power cap, and job allocations. And let's move on to the observations. We did preliminary evaluation using the real chip, A100 chip. The objective is quantify what aspects we need to take into account when we're doing our optimization, trying to get useful insights. And experiments are firstly, we try to do thorough scalability analysis, performance as a function of GPC. And also we checked the co-scheduling throughput analysis for different application mappings and memory partitioning options. As shown in the right figure, we can have different types of memory sharing option shared across collocated application, or we can set up in a private way. Okay, here is firstly Solran scalability analysis. In this case, we didn't do power capping, and we use two different options. First one is private one. So when we scale up the number of GPC, we also scale the memory resources. That is a private option. As for the shared option, we firstly allocate entire memory resources to the application, and then we scale up the number of GPCs. And we have for applications, and for this application, neither GPC allocation nor memory option matter. This is because that doesn't fully utilize both compute and bandwidth resources. And in this case, this is a streaming application. For that, memory option matters because it is memory limited. Also, it doesn't fully utilize computer resources. So in shared memory setup that saturate early, such as 3 GPCs or 4 GPCs, their computer intensive application scale very well, and memory option does not matter. And we also test Solran scalability while changing the power cap. Important finding is impact of power capping on scalability. It highly depends on what types of computation operations are used for the target application. The rightmost one actually utilizes tensor cores, and tensor core is a kind of power hungry module and affected the most by the power capping setup. So what we need to take the heterogeneity in compute resources into account, and we also test the co-scheduling throughput analysis for different memory sharing options and GPC resource allocation options as well. And in this case, we mixed computer intensive application and memory intensive streaming, and in that case, allocate more GPC to the compute intensive application is better, and also use the shared memory option is better, so that the streaming can access fully the memory boundless sources. And also in this case, they are not memory intensive application, so in that case, private setups is kind of better. That is because it is interference free, and also non-memory bound application may not fully use bandwidth. So this is a summary of the preliminary evaluation. So this is GPC allocation decision. Compute bound applications scale well and need more GPCs. And the power capping can affect the scalability, especially when using tensor cores intensively, and memory bound applications do not fully use GPCs when the shared option is used. And as for the memory partitioning decisions, if memory bound application is scheduled, the shared option is preferred. But if no memory bound application is scheduled, the private option can be better to mitigate the shared resource contentions. And here are the requirements for the optimization. We should consider application characteristics including memory intensity, compute intensity. That should be per different compute module, such as FP64, tensor core, etc. And also performance estimation should cover both scalability and interference aspects. This is the entire workflow overview that consists of offline part and online part. As for offline part, that determines model coefficients by using predetermined benchmark set beforehand. And for the online part, by using the model coefficients as well as application profiles, we try to optimize hardware knobs, resource partitioning, and power capping for a given application pair. So we are going to solve two problems here. One is trying to maximize throughput under fairness constraint. Application pairs are given, and power cap setup is also given, and try to optimize resource partitioning. And this is trying to maximize energy efficiency throughput divided by power cap under fairness constraint. Application pairs are given, and outputs are both resource partitioning setup and power capping setup. Here are more details of throughput and fairness. As for throughput, we use weighted speedup, which is widely used metric. Sum of relative performance of all collocated applications, that is a function of resource partitioning state and power capping. And this is a fairness metric. That is basically trying to limit slowdown within a certain level for all the collocated applications. And here is a performance modeling. We use a simple model using linear regression. This consists of a scalability part and interference part. And coefficients, in this case C and D, are functions of hardware setups and job allocations. And variables are based on the collocated performance counters, and that is transformed by using functions H and J. Here are the more details of performance counters and how we convert it to the variables. And here is the evaluation setup and experiment results. Workloads are Rodinia benchmark, and also we also use NVIDIA Catalyst library for gems, including tensor intensive kernels, and also streaming and random accesses, and classify them into four categories: tensor core intensive, compute intensive, without tensor, memory intensive, and unscalable. And here are the classifications, and create pairs of classes and randomly select an application for each class in each pair. This is how the exact setup and methodologies are. We firstly profile applications by using N-side compute framework and then train coefficients for all the possible hardware setups and job allocation. That means resource partitioning and also power capping, and obtain the estimated performance and choose the best job allocation for the two problems. And here is a model accuracy. In general, that is good for throughput and fairness for any partitioning state. And also, we observed similar trends for different power caps as well. And here is basically we optimize partitioning state for a given power cap and a given job pair. In the left figure, our proposal is very close to best. In this case, we set a power cap at to 30 watt, and we also scale the power capping from 150 to 250. And in most cases, our proposal is close to the best case. And we also did energy efficiency oriented optimization. We optimize partitioning state under a given power cap for a given job pair. As shown in the left figure, most of the case, our proposal is very close to best cases. And we also scale fairness constraint parameter from 0 to 0.4. And for most of the case, the proposal is quite close to best case. And here is the conclusion and future directions. So we target the optimization of resource partitioning, job allocations, and also power capping at the same time on a real GPU chip. And we provided some insights on scalability and resource sharing options useful for decisions on resource partitioning, job allocations, and power capping. And we proposed a systematic approach to optimize the above knobs. And we quantify the benefits of our approach that is basically close to the optimal. And future directions are one is including scheduling decisions. That means column pair selections from job queue. Include more hardware components such as CPUs, DRAMs, and multi-GPUs, etc. And also integrate with state-of-the-art scheduling software frameworks such as SLAM is a great option, I think. Okay, and that's it. Thank you very much.